With an understanding of energy conversions and energy losses due to resistance in fluids, we can look at the effect of resistance and pressure on volume flow rate. We'll use the Poiseuille equation for rate of fluid flow, that's volume flow rate. I'll use it mostly for blood flow in my videos. The first term we need to understand is volume flow rate. That's the volume of fluid that's going to enter our tube per unit time, per second. So let's say 2 liters per second. In other words, 2 liters of fluid is entering the tube in a second. The volume flow rate is determined first the pressure in versus the pressure out, and I'd recommend you draw these. Pressure in is the pressure at the beginning of the tube. It might be the pressure created by the heart, and the pressure out would be the pressure as it leaves that tube. In other words, that might be from an artery coming out of the heart and at arterioles going to capillaries. So liters per second, the pressure difference. Next term is pi over 8. That has to do with it being a tube, a circle. Next term is 1 over the viscosity. Now let's think about that. The volume flow rate, liters per second, makes sense, is proportional to the pressure difference. The pressure in minus the pressure out. That's the total pressure difference that's forcing fluid that can be converted into energy of momentum. And then the viscosity is slowing this down. The stickier the molecules are to other molecules, and they're sticky to the walls, the harder it is to move that blood through. So the higher the viscosity, the lower the volume flow rate. The next term is the radius to the fourth over the length. The radius to the fourth tells us that the radius has a huge effect. We increase the radius just from 1 to 1.1, we decrease the resistance by about 50%. So the larger diameter tube compared to a small one has lower resistance, and with lower resistance we get a higher flow rate. That lower resistance can be thought of as the effect of how close a typical molecule, an average molecule, is to the side. In a very narrow tube, this molecule finds it very easy to bump into the wall of the tube and lose energy to the wall of the tube. But in a tube of much higher radius, most molecules are bumping into other molecules. There's a much lower chance that a molecule will hit the side of the tube, less opportunity for molecules to lose energy to the outside of the tube. And then the last term is the length of the tube. A longer tube is going to have more resistance than a shorter tube of the same length. A longer tube has more chances for molecules to hit and lose energy. So we have the volume flow rate proportional to the change in pressure from in to out. The viscosity slows down the flow rate. The radius increases the flow, and the length reduces it. To understand this equation, we could sketch it as the difference in pressure in versus out, pressure at the beginning of the tube versus out, times the radius to the fourth, divided by the viscosity, stickiness of the fluid to itself, and divided by the length of the tube. I've redrawn the equation here with volume flow rate, difference in pressure, radius to the fourth, viscosity, and length. It has implications for blood flow through tubes. Here are 2 tubes, same pressure in, same pressure out, same length, and same viscosity of the blood. If the upper tube has 3 liters per second coming in, it must have 3 liters per second coming out. 3 in, 3 out in the same second. Must have a lower volume flow rate. Here's 1 liter per second coming in, 1 liter per second coming out. Thus, trying to force blood through a narrower tube with the same pressure differences, the same force produced by the heart, will move less volume of blood. Now let's look at what happens when we go from the same diameter at the beginning but narrow down. This part of the tube has a 1/6 cross-sectional area. That increases the resistance. Length is the same, viscosity is the same, change in pressure the same, but the resistance is higher. So we'd expect lower liters per second. Let's say it's 1 liter per second. That means instead of the 3 liters per second here, we only have 1 liter entering per second. In other words, the velocity is going to be 1/3, as in the upper tube. Watch what happens, though, as we convert the energy of momentum into energy of pressure in this transition area. Energy of momentum becomes energy of pressure, and that forces fluid under higher pressure into this part of the tube. Our 1 liter per second has to speed up. Here it's going at 1/3 the velocity up here, but now our 1 liter has to be stacked up into 1/6 the cross-sectional area. So we're 1/3 velocity here, but it's 6 times the initial velocity. In other words, the velocity here is now going to be faster than a velocity in our original tube. This should fit your understanding of what happens when you put your thumb over a garden hose and the water comes out faster. Here we have 1 liter per second coming out, but it's coming out at a higher velocity. So we've decreased the volume flow rate, but we've increased the velocity in this part of the tube. We've decreased it here. Now, in a heart often responds to constriction if there's not enough blood being delivered, lower volume flow rate, by increasing the pressure. So if we increase the pressure, then we change the pressure here. And we might actually maintain the same flow velocity despite the increased resistance. This equation allows us to predict the consequences of changes in a circulatory system. Here's a particular situation in which the arteries are a particular radius or total cross-sectional area, capillaries also, and veins, and we have 1 liter per second. We can predict that if we narrow the arteries, we're going to have below 1 liter per second when the capillaries and the veins are the same. In contrast, if the arteries are the same radius or total cross-sectional area, but we vasodilated the capillaries without changing the veins, we will have increased the radius and the capillaries. We've decreased the resistance. We'll have higher than 1 liter per second. The same logic should allow you to think through what will happen with any change in radius or, over the long term, viscosity of the blood, or when the heart compensates changes in pressure. Often when we have a change in radius because of vasodilation or vasoconstriction, the heart responds by increasing heart rate and heart stroke volume, increasing total output and total pressure, or decreasing